You know that feeling, right? You're coding away in Python, things are zipping along, but then as your data grows, your beautiful code starts to slow down, and then it crawls. It's a super common problem, and today we're going to pull back the curtain and find out exactly why that happens.
So this is the big question. It seems so simple, doesn't it? We're just adding one more little thing to our list. But what's really going on under the hood? Why does that one simple action sometimes have such a massive impact on performance? Well, we're about to find out.
Okay, let's get into it. To solve this whole mystery, we first have to understand what a Python list actually is, because the secret to its speed, or lack thereof, is built right into its core design. So that's the textbook definition, an ordered collection stored one after another. It sounds neat and simple, but that phrase, one after another in memory, that's the crucial part. That right there is both the list's greatest strength and, as we'll see, its biggest weakness. This is the only mental model you need. Forget all the technical stuff for a second. Just picture a long, continuous row of boxes, all connected. Each box holds one of your items. If you can keep this picture in your head, I promise everything else is going to click into place. All right, so we've got our row of boxes. Now let's see what happens when we start messing with it, when we add or remove things. This is where we really start to see why our code can suddenly slow down.
Okay, so check this out. If you want to add a new item to the very end of the list, what we call append, it's super easy. Python just grabs a new box and sticks it on the end. Simple. But what if you want to insert an item at the very beginning? Well, you can't just put it there. You have to literally shove every single other box down one spot to make room. And this chart says it all. Appending at the end is what we call O of 1, or constant time. It's crazy fast, and it doesn't matter if your list has 10 items or 10 million. But inserting at the beginning, that's O of n, or linear time. The cost grows directly with the size of your list. The more boxes you have, the more you have to shift, and the slower it gets. And really, it all comes down to this one simple idea. Shifting is expensive. Anytime you do something that forces Python to move all those boxes around, you're going to take a performance hit, especially on big lists. And it's the exact same story when you're removing items. Popping an item from the end? No problem. Python just gets rid of that last box. But if you remove an item from the beginning, now you've got this empty space at the front. And to keep that row of boxes connected, Python has to shift every single box to the left to fill in that gap. And no surprise here, the chart shows the exact same pattern. Removing from the end is a cheap O1 operation, but removing from the beginning is an expensive ON operation that just gets slower and slower the bigger your list gets. Okay, so we've got adding and removing down. But what about just finding stuff in the list? Let's see how our row of boxes helps us understand the performance here. So if you ask Python, hey, is the number 50 in my list? Python has no secret trick here. It literally has to start at box number 1 and ask, are you 50? Nope. Okay, move to box 2. Are you 50? Nope. It has to go box by box until it finds what it's looking for or gets to the very end. But here is where it gets cool. If you already know the box number, the index, you can just tell Python, hey, go get me whatever's in box number 200. And Python can instantly calculate where that is in memory and jump straight to it. No searching needed. It's like having a direct address. And I mean, just look at the difference here. It's not even a fair fight. Accessing by index is O of 1. It is lightning fast, always. Searching the list, on the other hand, is O of n, because in the worst case scenario, you have to look through the entire thing. Okay, so we've seen some things are fast and some are slow. Now it's time for the big reveal. When you're calling these simple list methods, you're not just doing one thing. You're actually running tiny hidden algorithms. So when you type a simple command like insert, you're kicking off a whole chain reaction. You're telling Python to run its built-in insertion algorithm. And what does that algorithm do? It goes through the painstaking process of shifting every single element over. That one simple line of code hides all that slow, hard work happening underneath. And that is the absolute key takeaway. The list method you choose determines the algorithm Python runs. When you choose append, you're choosing a fast algorithm. When you choose insert at the beginning, you're choosing a slow one. Understanding that connection is the real secret to writing performant code. So now that we've pulled back the curtain, let's make this super practical. let's boil it all down into a simple set of rules you can use every single day to keep your lists nice and speedy.
And here it is, your official cheat sheet for Python lists. The cheap, super fast OON operations, that's anything you do at the end of the list or when you access an item directly by its index. And the expensive, slow ON operations, that's messing with the beginning or the middle of the list or having to search through it. If your code is running slow, I'll bet you're spending a lot of time on that expensive side. And that's really it. The mystery is solved. It all comes down to avoiding those operations that force Python to constantly shift that entire row of boxes. So the next time you're writing code, you can ask yourself, am I working smart at the end of the list, or am I making Python do a whole bunch of extra slow work? The answer to that question will make all the difference.